new type of coordinates, and which we will call cylindrical polar coordinates. Now, whenever we define a new coordinate system, then we will link it with the Cartesian system first. We will explain it in terms of the Cartesian system, how we are defining these coordinates. So, you may have seen this coordinates in your physics course. So, let us say we have our Cartesian coordinates x, y, z, and we have the point P, which at time t is at x, y, z. Okay. So, now in cylindrical, in Cartesian coordinates, how do we write the position vector OP? That will be xi plus yj plus zk. Now, let me define a new coordinate system. So, first of all, this OP is my position vector r, and we know how it is in terms of x, y, z. What we do is, the first step in this polar coordinates is, we drop down from P, we drop a perpendicular down on the xy plane. That means we come down by z, we just fall from P on the xy plane. So, we take here and we drop down on the xy plane. When I do this, let me call this point as P star. I am not calling it P prime because we have called P prime something else. So, now what are the coordinates of the point P star? X, y, 0. Now, what I do is I join OP star. So, P star we drop vertically on the xy plane from P, and this intersects at xy plane at P star. Okay. Now, we will do some definitions. The length OP star, this will be defined as r. Okay. So, the length OP star is defined as r. So, notice this r, what we are defining is not the scalar magnitude of the vector r. The vector r, if its magnitude we look, that will be equal to square root of x square plus y square plus z square, whereas the magnitude of OP star is what? Square root of x square plus y square. So, therefore, we are not, this is not the magnitude of vector r. Okay, OP star. So, this is note, this is not the magnitude of vector OP or r. Then the angle which OP star makes with the x axis, I call this angle as theta. So, I have defined r, and the angle OP star makes with x axis, this is termed as theta. So, we have defined two new things, r and theta. Now, what I do is, a unit vector along OP star, this unit vector I term as ER. So along the direction of OP star, this is a vector, I choose something of unit length, one length, that is what I term as ER, a unit vector along R. And so let me show this now by maybe a different color. So a vector here of unit length is ER. I could place it anywhere, either at O or at P star, anywhere. It's a vector in that direction of length 1. Okay. So this is my ER vector. Now what will happen as the point P moves? As the point P moves, P star will also move. It could be anywhere in this plane. So therefore what will happen to the vector ER? Its direction will change, its magnitude will always be 1. So as the point P moves, the direction of ER will change. So therefore in that sense ER is not a fixed vector. Is that clear? So this is the vector ER. Then what I do is, so now I have defined vector ER. Next what I say is, perpendicular to ER in the xy plane in the direction of increasing theta is the unit vector which I term as E theta. That means in the same xy plane I go perpendicular to ER. So now if I look at perpendicular to ER here, I could have two possible directions. Perpendicular to ER is in this plane, could be these two directions, one going up, the other coming down. How do I choose the direction? In the direction of increasing theta. Increasing theta is up or down? Up. So that a unit vector along that direction, that means I choose up direction, and a unit vector here which is perpendicular to ER is what I term as E theta. Okay. And what we will realize is the z direction is perpendicular to both ER and E theta. So therefore a third unit vector in this case will be the vector along the z direction, which is the same as what we have called k, and we can call it Ez. So the third unit vector here will be the vector which is perpendicular to ER and E theta, which we will call as Ez, and which is the same as k. So the third unit vector completing the coordinate system is along z, and we call it Ez or k, same as k in Ijk. Okay. So these three axes which we have, r, theta, z, these are referred to as the cylindrical polar coordinates, and in this ER, E theta, Ez, they form a right handed triad. What is the meaning of right handed triad? ER cross E theta will give me Ez, E theta cross Ez is equal to ER, and Ez cross ER is equal to E theta. Obviously the dot product relations are there, that x ER dotted with E theta is 0, ER dotted with Ez is 0, all that follows. So this is a right handed triad. Now to work this out, so now let us give some names. ER is referred to as the unit radial vector. E theta is referred to as the transverse or circumferential unit vector, and Ez is referred to as the axial. There is another name we give to E theta, sometimes it is also referred to as the azimuthal unit vector. So, these are different names, ER, E theta and Ez. Okay. Now, can we relate ER and E theta to I and j? Let us come back to this picture. ER is a unit vector here. E theta is the unit vector which is perpendicular to ER in the xy plane. Now, in terms of theta and r, can I say what is ER vector in terms of I, j? ER is making an angle theta with x and 90 minus theta with y. So, therefore, ER can be written as cos theta I plus sin theta j. Is that clear? Straightforward? So, let us write that. So, ER is equal to cos theta I plus sin theta j. What is E theta now? If I look at E theta makes an angle of theta with y, okay, and 90 minus theta with minus x. So, therefore, E theta can be written as minus sin theta I plus cos theta j. Just think about it, that is what you will get. Now, one thing, whenever we write perpendicular unit vectors in this form, keep in mind that dot product has to be 0. So, when you take I dot I plus j dot j, cos theta minus sin theta cos theta, it will always add up to 0. So, that means when you write things in this form, you will either have one negative or three negatives. You can't have two negatives. Okay. So, just cross check once you write something like this, just do a simple calculation in your mind. I dot I is minus cos theta sin theta plus j dot j will be sin theta cos theta, it should be 0, which it is if it is done correctly. Okay. Now, let us do one more thing. Let us, since we have already done ER and E theta, let us find what is dER by dt. Let us take the derivative of this vector with respect to time. Now, as the point P moves, what changes? R changes, theta changes. Unit vectors I, j, k will not change. So, now when I differentiate this, theta could change. So, the dER by dt will become minus sin theta, theta dot I plus cos theta, theta dot j, and this becomes theta dot multiplied by minus sin theta I plus cos theta j, and this I can write it as theta dot multiplied by E theta. So, what I get is dER by dt is equal to theta dot E theta. Okay. Straightforward. Next, let us do the derivative of E theta. What is dE theta by dt? This will be minus of cos theta, theta dot I minus sin theta, theta dot j, this is equal to minus of theta dot common cos theta I what do you find? d Er by dt is parallel to E theta. d theta by dt is parallel to Er. Is this something expected or is this something that means derivative of Er is in a direction which is perpendicular to Er? Should this be expected or not?
Yes, sir.
Why?
Because if it has a component which is parallel to E theta, then it would change its magnitude.
That's right, because this is a vector which is of constant magnitude, and this will happen with any vector of constant magnitude. Suppose if a vector A has a constant magnitude, then vector A dotted with A, its direction may change, will be a constant. So if you take a derivative of A, so this will happen. So this is just a corollary, it's nothing to do with the this thing. I'll just show this. If you have a vector A which is constant in magnitude, then A dotted with A is equal to some constant k, and if I take the derivative of this, I get dA by dt dotted with A plus A dotted with dA by dt is equal to 0, and this tells me A dotted with dA by dt is 0, which means A and dA by dt have to be mutually perpendicular. If A dotted with dA by dt is 0, so then A and dA by dt is equal are perpendicular. So this implies A is perpendicular to dA by dt. But this will happen, and you gave the right physical reasoning for this. If the vector is constant in magnitude and if there is a component of dA by dt along A, then its magnitude has to change. So that was a very good physical argument which you gave, and I am just giving the mathematical argument for this. Okay. So now once we have this, then now we have all our ingredients. Let us now try to, so we have worked out the vector Er, the vector E theta. Now let us look at the cylindrical coordinates and how, what is the position vector of the point P. So let's go back to the old cartoon, this one. What is the position vector P in terms of our x, y, z in Cartesian coordinates? What was R, vector R? Xi plus yj plus zk. What is the vector R in cylindrical coordinates? Now in cylindrical coordinates, what do I have? R, theta, z. These are the three scalars, and I have three unit vectors Er, E theta, Ez. So what is the position vector R? R Er plus theta E theta plus z Ez, or no? Xi plus yj plus zk. So now the position vector is R Er plus theta E theta plus z Ez. Right or wrong? Wrong. Well, one reason why it is wrong is dimensionally it is wrong. Theta E theta does not have dimensions of length. So let's make it R theta. Will that work? No, let's look at it physically. We have to go to OP. So I can write it as OP star plus P star P. Fine. What is P star P? That's the simplest. Z Ez in vector. What is OP star? R Er. So that means in the position vector, theta will not come explicitly. So what is the position vector? R Er plus Z Ez. Simple. Just look at the picture. Don't go by anything else. Look at the physics. R Er plus Z Ez. Okay. So that is the position vector. So what happens to theta?
So it's an ER.
Theta is in Er because Er is a function of theta. That's right. So let's do this. So let's write the position vector. So let's now do the kinematics with cylindrical coordinates. Coordinates. So position vector R is equal to R Er plus z dz. So now we go to the velocity. I'll start on this page only. Let me write this again. And now you will see certain new things happening. dr by dt, which is equal to velocity. What is this? So let's differentiate this. This will be equal to r dot er plus r er dot plus z dot ez plus z ez dot. Okay. Now r dot er is r dot er. What is er dot? Er dot we have just seen. Er dot was theta dot e theta. So plus r theta dot e theta plus z dot ez. Ez dot is 0. So this is 0. So that's what we have. R dot er plus r theta dot e theta plus z dot ez. So these are the velocity vector. So that means what we have is v sub r is equal to r dot, v sub theta is equal to r theta dot, and v sub z is equal to z dot. So that's what we have. Okay. Next, let's go to the acceleration. So this is nothing very big here. In cylindrical coordinates, let's write the acceleration. So now we have to look at each of these terms and differentiate it properly. So first of all, r dot er, what does that give me? R double dot er plus r dot er dot. That's the first term. The second term gives me r dot theta dot e theta plus r theta dot theta double dot e theta plus r theta dot e theta dot. That is the second term. And the third term, z dot ez will give me z double dot ez plus z dot ez dot. I have differentiated each of the terms coming here. And now let's collect all the, let's see. So this becomes equal to r double dot er. Now er dot is theta dot e theta, so r dot theta dot e theta. Then we have plus r dot theta dot e theta plus r theta double dot e theta, and now we have minus r theta dot square er, and then we have plus z double dot ez. So now I will combine all the er terms together. This becomes equal to r double dot minus r theta dot square er plus r theta double dot 2 r dot theta dot e theta so I do this, and then this is what I get. I just differentiate these. So what I now get is the r theta and z components of acceleration. I get a sub r is equal to r double dot minus r theta dot square, and clearly this is not equal to r double dot. A sub theta acceleration is r theta double dot plus 2 times r dot theta dot, and this is not equal to theta double dot or r theta double dot. A sub z being the same old good old thing is equal to z double dot, and this is equal to Vz dot is equal to z double dot. Okay. So this is what happens in cylindrical coordinates when we write. Now once again let's keep the picture in mind. We have a point P which is moving. You take the origin, from origin you make the vector, you drop it on the xy plane, then the movement of this point in the xy plane gives you the movement of, gives you the positions r and theta. Okay. Now, so that means how one has to look at cylindrical coordinates is, it will always, so if we try to, this is the basically theory of cylindrical coordinates, but let's see how to use these in practical problems, because so in cylindrical coordinates we have these coordinates in this form. Now so in some problems what you will find is,
So these expressions would be given.
now there could be two type of problems. In one problem you need to use these, then they will be given. Maybe I will ask you to derive this, a 2 mark or 3 mark question in the lecture, in the exam. You are asking again, given you are asking for the exam, I assume. Yeah, so if that is so, then if I ask you to derive, then I will say okay, derive this, then again it will be given. So yeah, as long as, see, if you solve 3 or 4 problems you will remember them, but and also I will tell you a way of remembering it. So let's see, but before that let's see, in some problems what you will find is, you will find that r is given as a function of theta and z is also given, let us say, as another function of theta. Or in some problems you will find only z to be given as a function of theta, or in other problems only r to be a function of theta, z is some independent quantity which may or may not depend on theta. Now when you have things like this, then once again you have to be careful when you calculate r dot will be equal to df by d theta times theta dot, and z dot will be dg by d theta times theta dot, and r double dot, this is where the, this will be d2f by d theta square times theta dot square plus df by d theta times theta double dot. So keep in mind you have to differentiate each of these terms when you get to the second derivative, and similarly z double dot will be d2g by d theta square times theta dot square plus dg by d theta times theta double dot. So this will have to be kept in mind. Now before I move to the type of problems, let me just specify. Suppose if you have, if a point is moving in a circular path of radius r, and the origin is at the center. Let us first do this problem with origin at the center. So now this is, so this is basically cylindrical coordinates in a plane. There is no z component. In a lot of problems you will come across cylindrical coordinates with no z component. There may be a z component, there may not be one. So now if this is the situation, you have a particle moving on a circular path. So now if this is the point P, now let us try to see. What we have shown is that velocity is equal to r dot er plus r theta dot e theta. Now how will you find er? Er is the vector in this direction. If this angle is theta, this is how we will draw er and e theta. I join O to P, er is the vector along OP, e theta is perpendicular in direction of increasing theta. Now what do I get for velocity? R dot er plus r theta dot e theta. Now if it is moving in a circular path like this, what is r dot? So r is always in this constant equal to radius r. So that is equal to constant. So therefore what you get is the velocity is equal to r theta dot e theta. The same common sense knowledge which we know, we call theta dot as omega, so velocity is equal to r omega. No change here. Okay. Now I do the second thing, acceleration, I put in the formula r double dot minus r theta dot square er plus r theta double dot plus 2 r dot theta dot e theta. I am not copying it. Once I solve 2 or 3 problems, I remember this. Okay. So now let us try to see. In this circular motion problem, what is acceleration? What is r double dot will be 0. So this will become minus r theta dot square er, and this term will become r theta double dot e theta. And this is the same as we know if a body is moving in a circular path. The acceleration has 2 components, r omega square inwards. So this is r omega square, inwards means minus er, and plus r alpha. Alpha is nothing but d omega by dt or theta double dot. So what we know of typical circular motion is obviously followed by this. It had to. But now let us look at the same problem, and now in this let me use a red color. Suppose if I mark my origin at this O, the particle is again moving in the same path, but now if I shift my origin to this point, that means er and e theta are being measured with respect to this. So now what you will see is this vector OP which I draw, a vector in this direction, this will be the ER vector for the red color. So this is, or maybe I can call it as ER prime just to, so that there is no confusion, the red colors, because when you make a printout of this you will not get the color difference. So now, and the E theta vector is perpendicular to this, so this is E theta prime. Now in this new prime system, ER prime and E theta prime, R is not a constant. What is R given by? If you now try to see, if I call now this angle, this will be theta, I am just putting a prime to show it is a different theta. So now here you have 2r, small r prime will be given as 2r cos theta. So now if I shift my origin and measure, see the movement of the same point with respect to this cylindrical coordinates, r is now a function of theta. Whereas if the origin was fixed at the center, r was not a function of theta. Now if I am going to use this to calculate velocity and acceleration, I will get it in terms of ER prime and E theta prime. Okay, and then when I use this, now when I differentiate this, then r dot will not be 0. R dot will be minus 2r sin theta times theta dot, and similarly theta dot and theta double dot, and then I will work my accelerations like this. Okay. Now obviously if this thing is moving in a circle, and if it is something as simple, if there is no other physics involved, I would like to fix my coordinates here. When would I like to fix my coordinates here? Let me show that. Why do I take the second coordinates? Suppose I have, it could be a problem of that, or let me suppose there is a circular path here and I have a slot, and in the slot there is a ball which is fixed to the slot with a spring. So now this is a circular path, there is a ball which can move inside this slot, and this slot is rotating with angular velocity omega and angular acceleration omega dot. So this slot can move like this. In the slot we have a ball which is kept, and the ball will now trace this circle. Now in this case, what I will provide to you will be omega and omega dot of this rod. This rod is moving with certain speed, and now if I want to find velocity and acceleration of this point, a convenient way to do this problem would be to use cylindrical coordinates with this point as the origin. I could still solve the problem with this point as the origin. But then what I would have to do is, I would have to find the relation between this angle, and then which is just a twice, you will get it as twice, and then what you will have to do is relate the omega to the rate of change of theta dot. If you can do that, it's fine, but otherwise, if you are using cylindrical coordinates, then all you have to do is just write your formula. You write small r now is equal to 2 radius times cos theta, and so now if I am to solve this problem, omega and omega dot is given. If this is theta, this radius is r, then the first thing I would do in this problem is to work out, I will say small r is equal to 2r cos theta. This I will get from geometry. Then I will say r dot is equal to minus 2r sin theta theta dot. R double dot will be minus 2r cos theta theta dot square minus 2r sin theta theta double dot. This is r dot, and then I will put theta dot is equal to omega, theta double dot is equal to omega dot. And now once I do this, all I have to do is plug it in the formula, and then I will get velocity is equal to r dot er plus r theta dot e theta, and this will be equal to minus 2r sin theta theta dot er plus 2r cos theta into omega e theta. So this is I will get the velocity, and to get the acceleration I will just put in the formula again, r double dot minus r theta dot square er plus r is what, 2r cos theta r dot is minus 2r sin theta what I have done is I have blindly just written the expressions for r dot theta theta dot and put in these here to get the expressions. But now keep in mind that these velocity and accelerations I am getting are with respect to er and e theta, which has been defined in the figure. So then I can get the velocity and acceleration like this. So this is one example of a problem where we can use cylindrical coordinates and find the velocity and acceleration. I will do maybe one or two more examples, and then in the next class we will see path coordinates. Okay, thank you.